So for our next example, we see we have this next infinite series where the sequence that makes it up is 2n squared divided by e raised to the 1/4 n. And so what we're going to do here again is use the integral test. And so we can see just from this particular sequence the corresponding continuous time function that we want to use will be 2x squared divided by e raised to the 1/4 x. So here we'll say f of x is going to be equal to 2x squared over e to the 1/4 x. And so again, the three things that we need to check for is number one, we need to see is f of x going to be continuous on this interval from 1 to infinity. We need to make sure that f of x is going to be positive on this particular interval as well. And the last thing we need to figure out is f of x ultimately decreasing. So, of course, is it continuous on the interval from 1 to infinity? Yes, it is, because we know that 2x squared is a function that's continuous for all real numbers. So is e raised to the 1/4 x. So because of that, we know that the quotient of these two functions will be continuous for all real numbers as well. And because of that, and of course, it will be definitely continuous from 1 to infinity here. And also note that our e to the 1/4 x function will never be 0. So we won't have anywhere where the denominator will be 0. Thus, there's nowhere where this particular function will be undefined. As far as f of x being positive or it having all positive y values, we know that 2x squared, if we were to graph that for values from 1 to infinity, we would have all positive values here. And by definition, an exponential function must always have y values that are greater than 0. So, of course, this quotient is going to have all positive values as well. To show that this particular function is ultimately decreasing, if you remember, there was a couple of things that we could do. The easiest thing to do here is to note that we have a power function being divided by an exponential function. And so since exponential functions grow faster than power functions, we know that if we took the limit of this function as n approaches infinity, it would go to 0. Okay. So we know that this function checks all three boxes for the requirements to be able to use the integral test. And so now we're just going to use it. So here we're essentially just going to evaluate the improper integral from 1 to infinity of 2x squared divided by e raised to the 1/4 x. And so in doing this, if we know that this particular improper integral converges, meaning that it equals a real number, then we know that the corresponding series will converge as well. So for this particular integral that we're going to do, of course, we would have to do the limit. And since this is the upper limit, we'll say the limit as b approaches infinity of the definite integral from 1 to b. And here I'm going to rewrite our integrand because this is one where we'll end up having to do integration by parts on it. And so this is what it will look like. And that will be a negative there because we're going to bring up this e raised to the 1/4 x to the numerator. And so here we need to figure out what this definite integral is first. But of course, we want to do integration by parts. Now, it turns out that for this particular integrand that we're working with, this is one of those repeating integral type problems, or I'll call it a terminating integration by part problem. So here we could let this 2x squared here be the u, and we could let all this be the dv. And so since this is what I call a terminating integration by parts one, and it has this e raised to the negative 1/4 x in it, we can do tabular integration to kind of speed up the process here. So I'm going to go ahead and do that on the side. So here we're going to start off with 2x squared as our u, and we're going to start off with e raised to the negative 1/4 x dx for our dv. Now, in this column, we're just going to take successive derivatives. In this column, we're going to take successive antiderivatives, and we're going to stop once this u column here gets to 0. So here, if I take the derivative of 2x squared, that's just going to be 4x. Take the derivative of 4x, that's just going to be 4. And I take the derivative of 4, that's going to be 0. For the antiderivative here, I would have to use substitution rule to replace this negative 1/4 x with u. And when I do all that, what it ends up just being is that the antiderivative of e raised to the negative 1/4 x is just going to be e raised to the negative 1/4 x divided by a negative 1/4. So it's just whatever this is divided by the constant that is in that exponent there. And of course, 1 divided by a negative 1/4 is going to be a negative 4. So here this will be a negative 4 e raised to the negative 1/4 x. And so if we repeat that process, we're going to see that the next antiderivative is going to be 8 times e raised to the negative 1/4 x. And, sorry, that should be 16, not 8. Because it's basically being multiplied by another negative 4. And then the next one after that will be a minus 32 e raised to the negative 1/4 x. So since this terminates, we know that to figure out what the integration by parts would be for this, we can just do this whole diagonal thing and then go across. Of course, it's going to terminate at 0, so taking the 0 times this part doesn't matter. But we'll see that what we end up getting here is, once we do all of this, this will just end up being this 2x squared times negative 4 e raised to the negative 1/4 x. And so that would be a negative 8 x squared e raised to the negative 1/4 x. So this will be plus, and this will be minus, that will be plus. So this ends up being a minus here because of that. Here, the 4x times the 16 e raised to the negative 1/4 x, that will end up being minus 64. Be minus 64 x e raised to the negative 1/4 x. And we would have plus 4 times a negative 32, and that would be negative 128 e raised to the negative 1/4 x. And all of that will be evaluated from 1 to b. All right, so here we just need to evaluate everything at b, then evaluate everything at 1. So this will be negative 8b squared e raised to the negative b over 4 minus 64b e raised to the negative b over 4 minus 128 e raised to the minus b over 4. And so that will be what happens when we evaluate everything by b. And then we'll do minus and do the same thing and evaluate everything at 1. So in doing minus, we're just going to change the signs of all these. So this is going to be a plus 8 times 1 squared, e raised to the minus 1 over 4, plus 64 times 1, e raised to the minus 1 over 4, and plus 128, e raised to the minus 1 over 4. And we'll do some simplification there. And I'm also going to rewrite this differently too, so that when we evaluate the limit, it will be much easier for us to do. Let's get that looking right. So here we're going to have negative 8b squared divided by e raised to the x divided by 4, or e raised to the 1/4 x rather. So we have that, and this will be a minus 64 x divided by e raised to the 1/4 x minus 128 divided by e raised to the 1/4 x, and then this will be plus 8 e raised to the negative 1/4 plus 64 e raised to the negative 1/4, and then plus 128 e raised to the negative 1/4. And since all those terms are like terms, we could really just combine those together there. And so we'll have 64 and 8, which is 72, and 72 and 128 will be 200. So I'm just going to go ahead and rewrite all this here as just a plus 200 e raised to the negative 4, and erase all this other stuff here. All right, so this is what everything that is inside of our limit would actually end up being here. And all I have to do now is evaluate what I see here, evaluate the limit as b approaches infinity of that. And so we'll go ahead and close out with that. So therefore the limit as b approaches infinity of all this info here, and you can kind of see where this is going now. Have all this, and so whenever we execute this limit here, I don't know why I keep writing x there when it should be b, so let me fix that. Yeah, so like all these places here where I have x, this should be b. I don't know why I'm writing x for, but we'll go ahead and fix that right quick. There should be b here, b there, b there. Okay. All right, that looks a whole lot better now. And let's do the same thing down where I have things in black. So this should be b divided by 4. This here should be b there. And this should be b there. All right, so when we evaluate the limit here, of course, if we ignore the negative 8 for this first term, we'll have b squared divided by e raised to the 1/4 b. And we know that exponential functions grow faster than power functions. So we're going to have this situation of a -8, and then I'm going to write it out for this one, and then I'm going to simplify the answer later. So we'll have limit of b squared over e raised to b over 4. Yeah, I'll just make this simple. So eventually, because this function on bottom is growing faster than one on top, this whole term is going to go to 0 whenever I evaluate the limit. So this term will end up being 0 here because of that. This particular term also will be 0 because of that as well. And this term will also be 0 because of that. Okay. So these first 3 terms here would eventually be going to 0. And so the way that I'm going to write that here is I'm just going to say this is 8 times the limit . Not sure why I'm having such a hard problem with my pen today. So 8 times the limit of b squared over e raised to b over 4. And of course, this particular limit here, all of that will go to 0. Okay. And the same thing is going to follow suit for these other 2 because of the same reasons here. So again, just to kind of save myself some space here, I'm just going to rewrite all this in those first 3 terms. We know that the limit of that is just going to go to 0. So this is going to be 0 minus another 0 minus another 0. And then, of course, all we have left after that is the plus 200 e raised to the -1/4. Okay. And so the only thing that we're really concerned about here is the fact that 200 times e raised to the -1/4, that is a real number. And so since it's a real number, we know that this particular improper integral will converge. And because the improper integral converges, then that follows suit that this particular series also converges. Okay. So because the improper integral converges, we know that the corresponding series that we were considering here also converges. So for this next example here, we want to see if this series converges as well. And notice that the sequence that we're dealing with is 1 divided by some number raised to the n. And I know that we have natural log of 1.2 here, but natural log of 2 is just some number. So what's on the inside of here, even though it's not the same, is going to look a lot like 1 divided by some number. And I'm just going to say 2 here, raised to the n, just to make it simple. And so if we were looking at a corresponding series that looked like this, and we wanted to know whether it converged or not, the way that this looks would kind of trigger us to say, well, hey, we have something raised to a power here. This could possibly be a geometric series, okay? Because it kind of has the setup for that. And here, if I was to, rewrite this, of course, 1 raised to the anything other than infinity is just 1. So I could rewrite my numerator as 1 raised to the n, which means that I could actually have this going on now. And if I wanted to have n minus 1 here, I would have to break out that first term. So in other words, I would have to just do 1/2 times 1/2 raised to the n minus 1. And of course, that would be our summation here. And this would follow the profile of a geometric series because this is what the a would be. And we'll have r raised to the n minus 1. So the point I'm trying to make here is that just like we could set this up to be a geometric series, the series that we're actually asked to deal with is going to have the same type of thing going on. Okay, so here I could just say this is summation from n equals 1 to infinity, and this could be a 1 divided by natural log of 1.2. All that times another 1 over natural log of 1.2 raised to the n minus 1. Okay. And by definition, that would be a geometric series. And so where A would be 1 divided by natural log of 1.2, and R would be the same thing. So I'll just say that these are both equal to each other. All right, so now that we kind of have that in place here, I'm going to erase the example that I had, and then we'll finish this up. All right, so to finish this particular problem up, we know that we have a geometric series here, and all that we need to do is determine if this number R here, which is the same as A in this case, is in between -1 and 1. And so if you think about it, we know that natural log of 1 is 0. So natural log of 1.2 is just going to be a little bit past 0. So let's say, just to estimate, let's say it's like 0.2, just to be simple here. Now, of course, 1 divided by 0.2, that would actually end up being 5, because we know that 0.2 is just the same as 2/10. And here we said the reciprocal of 2/10 is 10 over 2, which is 5. So again, this is just an estimate here. My point is that this number, natural log of 1.2, is going to be a number in between 0 and 1, like 2/10 is. And so the reciprocal of any number in between 0 and 1 is going to be higher than 1. So my point here is that since this particular value here is going to be greater than 1, this implies that our geometric series is going to be a divergent one. Okay? Because of the fact that R here is not going to be in the interval that's from -1 to 1. So this means that this geo series diverges. Okay. And so the series that we're dealing with here just ends up diverging because of that. And so this is an instance to where I could have went through all the pain of trying to integrate this, but at the end of the day, I didn't really need to, because I recognized that it was a geometric series. And I know that we did an example earlier where I actually went through that whole process as well of doing the integration. But again, I want to let you know that if you recognize, hey, if you have a geometric series or a harmonic series, just go ahead and say that and save yourself some time. Okay. All right, so let's move to our next example. Okay, so for this next example here, we want to see if this particular series converges or diverges. And so here the same thing is, we have the 3 things that we need to check out. We need to make sure that if we're considering this function, the continuous time function analog of this, which would be 4 times arctan or tan inverse of x over 1 plus x squared here. We want to make sure that our function f of x is continuous, and this is going to be on the x value interval from 1 to infinity. We want to make sure that this function is always positive on this same interval. And the last thing we want to make sure is that our function here is ultimately decreasing. Okay, and I'm just putting ULT there for ultimately decreasing. And make that look a little better here. Okay. All right, so for the first criterion, which is this function going to be continuous? Well, we know arctan is a function that is continuous for all real numbers. And just in case you forgot what arctangent looks like, function looks something like this. This is x, this is y. And here, function kind of looks something like this. And we see that this function here is continuous for all values of x. Of course, 1 plus x squared is a parabola-like looking function. It looks something like this. It is continuous for all values of x. So therefore, the quotient of these two functions would be continuous for all values of x. So is f of x going to be positive for all values of x 1 and higher? Well, we see here that at x equals 1, our graph for arctan is going to be above the x-axis. And here at x equals 1, if we plug that into this function, of course, it's going to be above the x-axis as well. So both 4 times arctan of x and 1 plus x squared will both be positive values for values of x that are greater than or equal to 1. So we've met that second criterion as well. And so the third criterion is our graph of f of x ultimately decreasing? And so for this one, note that our tangent inverse function is trapped in between, I'm putting x there, but it really should be y. It's trapped in between these two horizontal asymptotes. Y is equal to pi over 2 and y is equal to negative pi over 2. So by default, the 1 plus x squared function here is going to grow faster than the 4 times arctan of x function. So our bottom function is going to grow faster than our top function. So as x approaches infinity, this function here is going to be approaching 0. So because of that, we know that our f of x will ultimately decrease. Okay, so we've checked out our the corresponding continuous function for our sequence that is making up this particular series, meets all 3 conditions. So we know that we can use the integral test. And so the integral test just basically says that we can evaluate this improper integral. And if this improper integral converges, then that means that the corresponding series will converge as well. So I'll go ahead and erase all this graph stuff here, and we'll just work on actually evaluating the improper integral at this point to see if it's going to converge. Okay, so I've gotten that stuff erased in. I kind of moved some things over a bit here. So we want to consider this improper integral, which basically means that here we're going to be rewriting this as the limit as b approaches infinity of definite integral from 1 to b for arctan of x over 1 plus x squared dx. And so we just need to evaluate that definite integral part. And so here, in order to do that, we could use substitution rule here. And so if we let u equal arctan of x here, then it means that du is going to be 1 over 1 plus x squared dx. So we see here that we have a way of being able to replace our integrand here in terms of u. So this would be just integral, and I'll deal with the limits of integration later here. But this will be 4 times u, because tan inverse of arctan is u. And then the 1, understood 1 over 1 plus x squared dx, that is just going to be du there, okay? Now, we also know here that for our limits of integration, that u of 1, if we do tan inverse of 1 here, this is just going to end up being pi over 4 radians. And of course, we know that because this is just like us asking the question, tangent of what angle is going to give you 1, okay? And we know that if we were looking at a right triangle here with this angle, we know that 1 square root 2, this is the quintessential isosceles right triangle. And of course, since this is 1 square root of 2, we know this is a 45, 45, 90 right triangle. And of course, that angle here would be 45 degrees, or pi over 4 if we thought about it in radians. So that's how we know that arctan or tan inverse of 1 is just going to be pi over 4. Now, we also know here that if we were to plug in b into this, then this will just be tangent inverse of b. Okay. And so what that means for us here is that our limits of integration are going to go from pi over 4 to tan inverse of b here. And let's try to get that looking nice, or nicer, I should say. So this is what we need to evaluate here. So of course this will be limit as b approaches infinity of, and if we do the antiderivative of 4u, that will just be 4u squared divided by 2, which is essentially just 2u squared. So I'll go ahead and simplify it to that. We'll change the way that this looks too. So kind of do this, 2u squared, and this will go from pi over 4 to tangent inverse of b. And so we can just evaluate. So let me get a little bit more room here. I'll go ahead and erase this substitution part to give myself a little bit more room. All right, so now that we have that, this will be limit as b approaches infinity. And now we're just going to be plugging in tangent inverse of b in for u here, and then pi over 4. So this will be 2 times tangent inverse of b, and that'll be squared, minus 2 times tangent, oh sorry, not tangent inverse because we've already done that. So it'll be 2 times pi over 4 squared. And so at this point, we just need to evaluate this particular limit. And essentially, we're just going to plug in infinity wherever we see b. And here, this will be 2 times pi squared over 16. And note here that the behavior of tangent inverse as it goes towards infinity, if you go back and look at the graph that we had, this is going to approach pi over 2, or that upper horizontal asymptote. Okay. So, in knowing that, this is just going to be 2 times pi over 2 squared, or let's say 2 times pi squared over 4. And then this will be minus 2 times pi squared over 16. And here we could, since we have a denominator 4, denominator of 16 here, we could make these like denominators. So if I wanted to make this first term have a denominator of 16, I would have to multiply by 4 here. So this would be the same as saying 8 times pi squared over 16. And of course, from here, if we do that, then this will just end up being 6 pi squared over 16. And of course, we can just simplify from here. We know that 6 and 16 both have a common factor of 2. So 2 goes into 6 3 times, and 2 goes into 16 8 times. And so this would be our final answer for that. And the main thing here is that our improper integral converges because this is a real number, okay? And so I'll write it like this. So since what we're dealing with here is a real number, this means that our improper integral converges, which also implies that the original series that we were asked about, it will also converge as well. And I don't know why I'm writing X when it should be N, but hopefully you get the point there. So we got N here, N there, converges. So we know that this particular series converges, and we know that that happens by the integral test. Okay, so for our final example here, we have the series, the infinite series from 1 to infinity for the counter n, and of course the sequence that is basically the foundation of this is going to be 2 times e raised to the 2n, all that divided by 1 plus e raised to the 4n. And so here I'm going to skip doing the checks and balances for the integral test here, just mainly because this one's kind of easy to see. Since we're dealing with exponential function divided by exponential function, we know that it's going to be continuous for all real numbers, so also be continuous from 1 to infinity. We also know that by definition, exponential functions will have to remain positive. And of course, these functions will follow suit in that. And of course, since e raised to the 4n is naturally going to be a function that grows faster than e raised to the 2n, we know that this function here is going to ultimately decrease. Of course, it's in sequence form, but if we replace the n's with x's, it'll also be that. So my point in saying is that we already know that this is going to work for the integral test. So we're just going to use the integral test, which basically says here, if we evaluate this improper integral, and it converges, then we know that the corresponding series will converge as well. So basically we just need to integrate this. And again, we're going to do limit as b approaches infinity of our definite integral from 1 to b, 2 times e raised to the 2x dx over 1 plus, and I'm going to rewrite this e raised to the 4x as e raised to the 2x squared. Okay. And the reason that I'm doing that is because I suspect in how this looks that I could use a substitution rule to help me be able to evaluate this definite integral here. And I know that if I have this as e raised to the 2x, the derivative of e raised to the 2x is proportional to itself. And I see that I have that here in the numerator. Okay. So I think it'll work out if I do substitution here. So in this case, let's let u equal e raised to the 2x. And if that's the case, then if we take the derivative of u, that's going to be e raised to the 2x times 2, because of the chain rule, times dx, which is essentially what we have in the numerator here. So we know that all of this will basically be replaced by du. We know that what we see here is just going to be replaced with u. And so now all we have to do is figure out what our limits of integration look like in terms of u. Okay. So also here we'll say u of 1. And if we plug in 1 here for x, that will just be e raised to the 2. And u of b will just be e raised to the 2b. Okay. So with all that said here, basically what this means is that now we have limit as b approaches infinity of, and now we're going to write everything in terms of u. So we have integral, and instead of writing a 1 here, we do u of 1, which is e raised to the 2. And instead of writing b here, we're going to write e raised to the 2b. And for our integrand, we're just going to have du over 1 plus u squared. Okay. All right, and so if we look at what we have here, this should look kind of familiar to us. This is the same as just saying 1 over 1 plus u squared du. And we know that the antiderivative of 1 over 1 plus u squared is just a tangent inverse, or arctan. So here, let's say limit as b approaches infinity. The antiderivative of this is just going to be arctan of u, and that's going to be evaluated from e squared to e raised to the 2b. Okay. And so for here, all we need to do is just plug in our limits of integration here according to the net change theorem. So this will be arctan of e raised to the 2b minus arctan of e squared. And so here we know that at this point we just need to evaluate this limit here, and basically we're going to plug in infinity wherever we see b. And if we have arctan of e raised to the 2 times infinity, that's just going to be e raised to the infinity. And this will be arctan of e squared. Now, arctan of e squared, that is just going to be some number. We don't know exactly what number that is, but it's just going to be some real number, and that's all we care about. Here we know that e raised to the infinity here, that will just end up being infinity. And the behavior of arctangent, as the values, in this case of b, go to infinity. If you remember, arctan is a function that looks something like this. So as we're going to a value of b approaches infinity, it's approaching this horizontal asymptote here, which would be y is equal to pi over 2. Okay, so the point here is that we know that this result is just going to be pi over 2 minus this arctan of e squared. And we know that this is a real number. And so since it's a real number, we know that this corresponding improper integral converges. And so since the improper integral converges, we also know that the corresponding series will converge too by means of the integral test. And so this is our final example on the integral test. And I'm hoping that not only you understand how improper integrals sort of play a role in helping us to be able to determine whether a particular series converges or not, but hopefully this video also has helped you be able to analyze sequences in their corresponding continuous functions to see if they even fit the bill to be able to have the integral test be used on it. All right, so I will see you in the next video. For those of you that are kind of watching these in order, the next set of videos that will come after this will be the ones on the comparison test. So I hope to see you there.